This example, we want to look at the set given by capital S equal to 1 cosine of x, cosine 2x, cosine 3x, 4x, cosine 5x, sine of x, sine of 2x, sine of 3x, sine of 4x, and sine of 5x. Okay, with respect to this norm, where the inner product of v1 and v2 is equal to the integral from 0 to 2 pi of two of the functions being multiplied together. So it's that integral that is the norm for this set. And we want to show that S is orthogonal, is an orthogonal basis. So what that means is we need to take each element of this set and see if this condition is satisfied. Specifically, we want to see if for every I not equal to j, if the integral between them is equal to 0. If it's true, then for each of the elements chosen, then we will see that when I is not equal to j, that integral is 0. Okay, we're going to switch over to some technology right now to show that this is indeed the case. As we look here at this setup, n is going to be our index as we go through. We're looking at our limits of integration from 0 to 2 pi. And our sequences here are going to take care of all of the integrations that we need to account for in the norm we described earlier, okay? Which you can see here is the integral from 0 to 2 pi. So in this first one, we're looking at all of the cross terms. So any of the cosines times any of the sines. We're looking at that product to see if it indeed is, if any of them give us a non-zero answer. In the next case, we're looking at the products of when cosines are only multiplied together. So n is going to go from 1, 2, 3, 4, well, starting at 0. When cosine is 0, this is 1, and this is 1. So the integral of this first case here actually is the case when it's the 1 being multiplied together. So this is actually, these are both 1s, and so you see there that that integral is actually not 0, but it shouldn't be because the element there is 1. Okay, so it should make sense. This is 1, 1, right? This is the integral from 0 to 2 pi. So it's integral of 1 over 2 pi, so that should be 2 pi. Okay. And this is the integral for sine, where the sine indices are different. And there will be one example when n is equal to I, which should be the one non-zero case. Okay. They are both 0 in this case, even though both I and j or n are here equal here. The reason being is because sine of 0 is 0. So the integrand is actually 0 at this point. Okay. So we're going to index through I, and as that sequence grows, what you're going to see is, so for n equals 1, okay, the cosine term and sine term, that product, are 0, and they'll be 0 for each value of n, no matter if I and j are the same, or I and n are the same. Cosines and sines are always going to be orthogonal on this basis or on this norm, okay? And you'll see here that when cosine and cosine have the same indice, they have a non-zero value. Likewise here for sine, okay? That's when I equals j in the norm. If we go to the next term, okay, you'll see here the last one is where I equals j. When the sine and cosine are together, they're 0. When cosine and cosine are together, it's a non-zero term for the case when the I and j are the same and 0 otherwise. And so if I go through each of these 4, okay, that takes care of every possibility, with the only non-zero integrals coming from when I and j are equal, or I and n in this case are equal to each other. Okay, so that shows then that this is an orthogonal basis with respect to the 11 elements and this norm. For part B, what we're looking at is the function g of x equal to x minus 3 square roots of x. We want to write this as a linear combination, or as in terms of the new bases. Since our basis set we just showed is linearly independent, then using our previous theorem, to write it in terms of the function, what we're going to do is we're going to take the weight of g and how each contributes to its new coordinate. So g, the inner product of g and a0, this is that case when a0 is really just the 1, that first unit in or the first value. And so this is when this is cosine of x, cosine 2x, cosine 3x, cosine 4x, and cosine 5x. sine x, sine 2x, sine 3x, sine 4x, and sine 5x. So each of these, the a1, the a5, the b5, those are all the sine function or cosine. So a is cosine, b is sine, and the values you see here, we have to compute each of these integrals. We have to compute g of x times the sine of x over the interval from 0 to 2 pi. That's this integral, and then we're going to divide it by the norm or the length or the magnitude, if you will, of b1, which is b1 of sine of x times sine of x. So sine of x squared over the interval. And so we're going to do that for each of these terms. So you can see we have several integrals to compute, and then we multiply that weight times the function to determine how much weight does each of these terms provide for that particular vector, and the sum of which will then be equal to g of x with respect to the new basis. We're going to use technology to accomplish this task, so let's switch over there. Just like in the last one, we're going to utilize GeoGebra. So we just saw from our work here that GeoGebra is linear, or GeoGebra showed us that the integrals are factor orthogonal, which according to our last theorem allows us to write this as a basis. And so here we're computing each of the coefficients, the weights, if you will. And I call each of these then the factor, and then I multiply it by the vector. So each of these actually is a vector with the weights in front corresponding to then the calculation. You could think of these as like the coordinates under the new vectors. How much of this I need along this direction? Okay, so calculating each of these, I define the function g of x. So there it is. And then as we scroll down, you can see how I'm calculating each of the weights, just like I showed you on what I'd written out earlier. And so once I've done all of that, then I finally define the function. And so here you see how I have a0, which was so this is just the shorthand version of what you saw written out with the actual computations carried out. Okay, so carrying this out in total then gives us the representation of g of x with respect to this new basis. To kind of come see how well this does, let's look at the graph of it. And you can see here, the blue line is g of x. That's x minus 3 square roots of x. And it kind of goes like this. And this is over the interval from 0 to 2 pi, so right around here. You'll notice that the green function, which is our representation of g of x under this basis, here you can see the f kind of floating off over here. So you can see it doesn't quite get it to it until a little bit after the function, but it does a reasonably good job of approximating g of x on this interval, but with the endpoints having a little bit of flaring off. You'll also notice that if I zoom out, the interpretation of g of x is you're seeing a periodic extension since our interval is defined for 0 to 2 pi. That's the length of the interval which the period of that function is. So it does a reasonable approximation. There is a very particular discussion about the endpoints and the wiggle room that you see here, which we'll talk more about in another video. Anyways, I hope you can see that this was a pretty good approximation. And while computationally a little bit difficult, with the use of technology, it makes it certainly a lot more manageable. All right, I hope that was helpful, and I'll see you in the next video.